When we picture the birth of the digital age, we usually imagine mid-century laboratories packed with humming machines and sprawling wires. The physical architecture of those machines is incredibly complex, but the digital world they process relies entirely on two simple concepts: binary logic, ones and zeros, and the mathematical void. We tend to picture engineers in lab coats as the sole architects of these ideas. The true inventors of this digital blueprint were ancient Indian scholars, mapping the rhythms of poetry and the cosmos millennia ago. Around the 2nd century BCE, a scholar named Acharya Pingala set out to map every possible rhythmic structure in Sanskrit poetry. He documented this exhaustive work in a treatise called the Chandaḥśāstra. To map these rhythms, Pingala divided speech into two distinct beats, short, called lagu, and long, called guru. By calculating how these simple beats combine, he created a formal binary number system centuries before European mathematicians. This table shows the number of structural forms a poetic meter can take, derived directly from Pingala's algorithms. By calculating these rhythmic possibilities, he formulated the principles of combinatorics, creating the exact numerical structure the world would later call Pascal's triangle. Pingala successfully charted the binary logic of the one, but the world could not yet compute because mathematicians lacked a functional understanding of the zero, the void. By 628 CE, the Indian astronomer and mathematician Brahmagupta formalized the rules of zero. Other ancient civilizations, like the Mayans and the Babylonians, had a concept for zero. They used it as a blank space, a positional placeholder to tell the difference between a number like 1 and 100. Brahmagupta took a different approach in his text, the Brahmasphutta Siddhanta. He codified nothingness itself, establishing zero as an independent functional number that sat precisely between positive units, which he called fortunes, and negative units, or debts. He laid down the specific arithmetic rules for this new number, proving that zero could be actively added, subtracted, and multiplied. If you subtract a number from itself, you get zero. By defining the exact operational rules of zero, Brahmagupta provided the stable mathematical platform necessary for higher branches of mathematics, and eventually machine computation, to exist. Through trade and scholarly exchange, these Indian mathematical systems began to migrate westward. They reached the scholars of the Islamic Golden Age in Baghdad, who quickly recognized the efficiency of the Indian numeral system and embraced it for their own calculations. The Persian mathematician Al-Khwarizmi translated these ideas for a wider audience, standardizing what the world would eventually call Hindu-Arabic numerals. In the 13th century, an Italian merchant named Fibonacci brought this counting system to Western Europe, championing its use for trade and bookkeeping over older, bulkier methods. This global relay of ideas replaced the cumbersome Roman numeral system across Europe, providing the exact mathematical tools that fueled the advancements of the Renaissance. Fast forward to the present day, when modern computer scientists adopted binary logic to build the first digital machines, they implemented a logic system with ancient roots. The physical components of a computer, the silicon, the wiring, the electricity, are entirely modern, but they exist merely to execute ancient mathematical rules. Every line of code, every software program, and every digital file relies on the exact same dual rhythm Pingala charted for Sanskrit verses. The artificial intelligence and digital technologies you use today are the direct, living legacy of an ancient human attempt to understand art, poetry, and the cosmos. Follow Roots of Routine for more histories of the hidden ideas that built the modern world.
Subscribe to us for more such videos.